Thank you for the opportunity to talk about this project. And it's been a lovely day. I turned up yesterday and I've had a lovely time. I think just a bit of an introduction as to my research and my research group, because I'm really new to this network, but we're interested in all aspects of nanomaterials, making them in a variety of different ways. We're excited about exploring the fundamental properties of these materials and relating it to how they're made. So we're interested in applying nanomaterial research to the real world, and to do that, it's really nice if we can understand the relationship between how it's made and then how it performs. And one of the things we're really interested in is exploiting automation, self-optimisation and AI to do that. So we sort of draw an analogy from where I work in the IPRD, where we do a lot of process optimization, where we take a material, we try and make it, we try and catalyse it, we look at what we get in terms of the final product, and then we go through an iterative cycle of either self-optimisation or statistical sort of design of experiment space exploration. And my role when I was brought into the IPRD was to look at the materials that are doing the science. And what we're trying to do is we're trying to evolve the catalysts or the nanomaterials so that that can be a second feedback loop. So we're making materials that then make better processes. And we work with a lot of different companies. And I do it really briefly, but my group spans a lot of different areas. We make nanomaterials, a variety of different length scales and different dimensions. We characterize those in new and advanced ways, and also sort of off-the-shelf methods. We use a lot of automated continuous flow, which will be part of this talk. I do a lot of heterogeneous catalysis work, which is what companies are interested in from my group's perspective. And then we also make a lot of applied nanomaterials. So we've had a bit of traction recently with a diverse set of materials, redox flow battery charge carriers based on fullerenes, nanowires for sensing, and also quantum dots for a variety of different reasons. But today I'm going to talk about self-optimisation, and we've got a video here from one of our EPSRC projects that was sort of commissioned, and it kind of, hopefully it goes through what our sort of research process is. But basically we have continuous flow reactors where we have pumps, a reactor, and online analysis. And what we do is we feed our conditions into the pumps. They generate a reaction, so we mix our products, they go through a reactor. You can see here, we can control the temperature of that reaction, and we get an output, a reaction, a chemical reaction that then goes into some online analysis. And again, we have lots of different reactors and we have lots of different online analysis, but we read a product out. That product goes into a computer. The computer takes that output, in this case it was the amount of product, and then it works out what the next reaction should look like, what the next temperature should be, what the ratio should be, and then it looks at the product that we form from that, and then it goes back round and round and round. And the AI component is the computer generating the different products, and we use different types of algorithms to analyse the relationship between conditions and products, and we eventually come up with a model, either a kinetic model of the system or a map of the parameter space. And you can see here, this is an AstraZeneca product that we managed to optimise the synthesis of. But basically our output is process understanding in a better system. So what this project was about, and an area we were interested in this project, was nanoparticles synthesis and catalysis. And previously in the group, we'd optimised a nanoparticle catalyst, and we used that in a series of reactions, and in this case it was a nitrophenol reduction, and we used the catalyst off the shelf, and we optimised a nitrophenol reduction, and we explored all the different conditions of that reaction using a standard catalyst, and we ended up with an optimised system. And we also had a kinetic model for that system, which we then predicted on a kilo scale batch reaction. And you can see on the bottom right hand side the dots are the experimental measurement of the kilogram scale reaction, and the line is our prediction. So it married up quite well, and we got good process understanding. And that was published last year. And what we're interested in this project is a bit more evolution of that idea. So in this case, we take the nanoparticle synthesis, the catalyst synthesis, we do that first, and then we telescope it into a second reaction again that we're interested in catalysing. So we're using this telescope process to develop a catalyst that is perfect and specifically designed for the reaction of interest. And this is an interesting optimization problem. There are lots of things going on here. And the first thing we did was to make sure we could make nanoparticles in flow and in a controlled way. And this is our system, is a schematic on the right-hand side. But basically we explored gold and silver nanoalloys. And if you look at the bottom right, we can basically make gold and silver nanoparticles alloyed in any ratio we like. The different colours, the yellow ones are silver, the really dark red ones are gold, and we can get any ratio in between. And if you look at the bottom left, you can see they're the different steps, the different alloyed steps in 10% steps, and you can see the UV-Vis trace allows you to monitor what you've made, and you can see that we can get to steady state and controlled synthesis of these materials. So what we wanted to do is explore this system, we wanted to optimise it, and there are lots of things to do, and it's a good challenge. What variables are we interested in looking into? How do we treat those variables? So for example, you can treat some variables as continuous or discrete. So continuous variables in our case are things like temperature, reaction time, anything that can be a continuum. Discrete variables are typically solvent, catalyst, things that are binary. Because of our nanoparticle alloy system, we can either treat it as a continuous variable where we go from anywhere from 0 to 100% silver and gold, or we can treat it in stochastic steps, and we were interested in exploring that. And from a telescoping perspective, we're interested in looking at two-stage processes, and there's quite a lot of work in the group doing telescope systems for pharmaceuticals, and we wanted to know whether we should treat both systems independently or do the whole optimization together. And we decided for simplicity that we were going to just look at one step at a time to start with, and in this project we'll do that. So in terms of probably most pertinent to this audience, we were looking at how to manage discrete and continuous variables within a single optimization. And we published something last year about mixed variable optimization, where you can mix discrete and continuous variables in a single optimization. And it's not as easy as you'd hope, because when you're doing an optimization, you need to understand the interconnectivity of the different variables. And if they're all continuous, you can always measure a distance between them. But if there's some discrete variables or some continuous ones, it's hard to treat them both in the same way. So what we did, and we published it last year in collaboration with Professor Richard Bourne and Jamie Manson, who was the PhD student, we used a Gaussian process to measure the distance between the different variables. It's nice and easy for continuous systems, but it became difficult for discrete systems, because how do you compare one catalyst with another, for example? And what we decided to do was use Gower distances, and we used two mathematical formulas. For continuous variables, we just used the distance between the two. But for quantitative or qualitative variables, we just basically describe the distance between the same catalyst as 0 and any other catalyst that's a different make to be 1. And how that looks in a real system is like this. So this is the experiment we used and published in this example. We have different temperatures, we have different solvents, we have different residence times. So that's two continuous variables and one discrete one. And if you look at the different color coding here, we normalize the distance between the temperatures on the continuum, the residence times on the continuum, and then the solvents in a binary system where it was 1 and 0, and then we added those Gower distances together. And you can see from a combined system, you get a 1 to 0 normalized distance. And what that looks like in real terms, we demonstrated with this reaction here, which is our test reaction for quite a lot of different systems. We take this reaction and we look at the selectivity of ortho versus para. You can see here from this morpholine unit. This was the reaction scheme down the bottom. But what we end up doing, this is the lab system. So we've got several pumps, a reactor in the middle and an HPLC online. But you can see what you can end up doing is you can understand the relationship between ortho and para as in relation to the temperatures, the conditions and the solvent we used. And you can see here we have 6 different solvents that this system explored, and you end up generating a front here between the payoff between reaction yield of ortho and para, and you can see it bunches up into different solvents. So it's a really powerful system. I appreciate I'm going quite quickly, but I want to get to sort of what the AISD project was about, and this was Louis, who came to work for me over the summer. He got trapped in Germany by COVID because they moved all their exams into the summer, so he was only with me for 6 weeks. But he did a remarkable amount of work in that time, and he's a really able student, actually. And what we got him to do was to simulate the use of gold and silver ratio as a discrete variable, which simulates what normal, typical catalysis people would do, which is make 10 catalysts, stick them on a liquid handler, and then drip them in. And we got him to calculate and optimize the system in silico using that as a system to understand how many catalysts we'd need to make compared to a continuous approximation of that catalyst, and then we got him to perform some of these optimizations in the lab. So to do that, he used this algorithm that we've developed in the group, and he used the kinetics from the system in flow that we'd already found. So the first thing he did was he took linearly spaced discrete variables from 0 gold to 100% gold in different levels. So he worked from 5 to 21 levels in different steps. And you can see that the cumulative conversion, or the way that it optimized up to a maximum yield of about 65%, varied depending on how many levels the optimization had to explore. Clearly, if there are more levels it could possibly explore, it took a bit longer, but it always got to the same optimum. What he also was aware of, and we knew from the beginning, is that the more gold you put in, the better it is to some extent. So he also explored spacing the levels exponentially towards a higher gold weighting, so that there are more gold containing catalysts than silver containing catalysts, and he did exactly the same thing. So he went from 5 to 19 in this case. And again, we saw a similar trend. So the sort of summary of his work is that if you explore linear and exponential discrete steps of algorithms, you get to the same optimization in each case, which was 100% gold, and linear is quicker than exponential for no real reason that we could understand. But the thing we really wanted to get to is how does it compare to doing it continuously? And sadly, it's quicker to use discrete variables, but you don't get to the maximum optimum yield, which is 73% for the continuous system. And that's linked, unfortunately, to the fact that he could only ever get 21 discrete levels to work in his computer before his computer fell over and couldn't cope with the amount of processing. And it wasn't necessarily a problem with his computer. We did also use a supercomputer. It's just there's literally too much data to crunch. So though that feels a little bit trivial, it's actually quite an important limitation of our code, which we now found out, which was quite a finding. He also performed, because he was keen to do some experiments, he also performed the continuous variable reaction in the lab, and this is the optimization here. You can see it gets to a yield of 73% over 70 experiments, and what that system looks like is this. So this is a series of flow reactors. The first thing is a series of CSTRs where you make the nanoparticles. There's a reactor coil here that stores the nanoparticle catalyst of your design, and then you bleed it into this second system. So you take the nanoparticles, you form them in this coil. When they get to steady state and then what you want, you then switch them, and then it goes through this second reaction, which tests the reactivity of that system. So if you look at the process here, you can see the blue is the UV-Vis trace of the catalyst being made, and when it gets to steady state, i.e. it plateaus and it's consistently what you want, you can then trigger that reaction, and it goes through the second coil into your nanoparticle catalysis. And then the red trace is the catalyst working and forming the product. And you can see again, when you get to the plateau of the red, you trigger it and you get a HPLC for that reaction data. And again, this reaction, I can't add it up, there's about 20 here in about 2.5 hours. It's quite a quick system. We did some optimizations. The first one we did was with something called snob fit, which I can explain offline what it is. But we explored between 0 and 1 in terms of gold to silver, so 100% silver all the way to 100% gold. We found quite quickly that it's more gold that's important, so we zoomed in this area between 90% gold and 100% gold, and we actually found that 97% gold is the optimum. We then explored the fixed conditions across there again from 90% gold to 100% gold, and you can see here, I don't know whether you can see my screen yet, this is the optimum here between 97 and 98% gold. We captured all these materials to check that the nanoparticle size was the same in all of them, and you can see it pretty much is. So the nanoparticle size is consistent, but the catalysis favours this 97 to 98% gold. We also very quickly explored the different algorithms. So we explored snob fit versus a Bayesian algorithm, which again I can discuss offline if people want to, but as people know, I think I'm found quite consistent with Bayesian optimization. You get to the maximum or the optimum quicker. And we saw that here. If you can see here, we get to the optimum after 10 experiments in our system versus about 25 with snob fit. But again, you have a trade-off. The Bayesian optimization has explored less of this chemical space. So we're understanding our systems quite nicely. So that's my summary. In summary, we've managed to create a nanoparticle synthesis self-optimization system using the performance in a reaction as the objective. Clearly, if you want to make a catalyst, how well it performs is the #1 criteria. We can also do multi-objective screening to understand the cost of these materials and their environmental impact. But we've got a good handle on these systems. It's nice and stable, so we can pretty much leave it running forever, which is nice, as long as you can afford the gold. And we've explored discrete versus continuous approaches for nanoparticle composition. And basically, if you can make your nanoparticles in a continuum, it's preferable because the maths is easier for your computer. Next steps, we're looking at telescoped optimisations, both in this system and other pharmaceutical systems. And we're also looking at process understanding and scale-up. So we've just started an EPSRC grant called NanoMan, which is looking at polymer nanoparticles for drug delivery and quantum dots for screens, trying to make them in a sustainable way and then scale them up using process understanding. So that just leaves me to thank everyone in my group, especially Louis and Brendan, who did a lot of work on this. And there is a big team of people in Leeds, both in my group at the top and then the IPRD, which is the bigger institute. The Yorkshire Dales is nice if you have the chance to come. It's lovely and it's always sunny. And that just leaves me to thank all the people from Money, especially obviously the AI4SD for this and the opportunity to speak. So hopefully that's